Okay, welcome back. Welcome to week 2, lecture 2. We finished lecture 1 talking about various ways of creating Numpy ND arrays. I've backed up a couple of slides here to do a little bit of review. So here's slide 17. We can create an ND array in Python by using the np.array construction function, and we can give any so-called iterable object as an argument to this np.array function. We can create one-dimensional arrays by giving for example, a one-dimensional list or a one-dimensional tuple, or for that matter, a set. We can also create two-dimensional ND arrays by giving, for example, a list of lists. Or we can create three-dimensional arrays by giving a list of lists of lists, or a tuple of tuples, and so forth. We took a look at the shape attribute. The shape attribute is always a tuple representing the lengths of the various dimensions. So even if the array is a one-dimensional vector, we still get a tuple back telling us how many items there are in that one dimension. We can use the ndim attribute to find out how many dimensions the ND array has. And we can use the dtype attribute to find out what the data type is of the items in the ND array. In the ND array, all of the items have to be of the same type. So if you give a list of lists of all int values, you will by default end up with an ND array of integers. On slide 19 here, we're showing int64 as the data type. On my system, and I suspect on your system, you will get an int32 by default. So that's just a 4-byte wide, a 32-bit integer value. But you might get an int64, which would be an 8-byte wide integer value. If you have one or more floating point values in your list of initial values, then everything is going to be upgraded or upcast to floating point. All right, we also took a look at using .t to get the transpose of an ND array. Other ways of creating ND arrays are zeros to get an array of all zeros, or ones to get an array of all ones. Notice that if you want a multidimensional array, a multidimensional ND array, you have to use a tuple to express the shape that you want the resulting ND array to have. So we can create a 2x4 ND array of zeros, a 1x4 ND array of ones. We can also create identity matrices either by using the EYE method, or by using the identity method, and we just specify, since in these cases the arrays have to be square, we only need to specify one dimension. As opposed to 0 or 1, as opposed to zeros or ones, we can create an array having an arbitrary value as the initial value of all of the elements by using the full function, right? So here we're creating a 2x2 ND array of all 5s, or a 1x3 ND array of all 2.7s. Now, just like with zeros or ones, I actually get floating point data types for all values by default. So even though I've said give me a 2x2 ND array of the value 5, by default that gets represented as the floating point value 5.0. Now, I actually ended lecture 1 before we got to this yet another way of creating an ND array. And this is the aRange function. It's somewhat similar to the range function that we can use in a loop or in a comprehension to step through a sequence of values, 0, 1, 2, 3, whatever. If I say NP, let's see, we're going to create array 8 here. NP dot, gets NP dot dot aRange 6. Okay, well, aRange 6 is basically the same as if you had typed out the list of values 0, 1, 2, 3, 4, 5. And so the upshot is that array 8 is going to be an ND array of values 0, 1, 2, 3, 4, 5. And notice that these are integer values by default. If I had said array 8, let me say B, gets np dot aRange 6.0, then array 8b now has floating point values in it by default. To the aRange function, you can actually give up to 3 arguments, and these will be used in the same way that they're used for the ordinary range function. That is, the first argument specifies the starting value, the second argument specifies the, beyond the end of the range of values, and the third argument, if you provide it, is the step size. By default, the step size will be 1 if you leave out that third argument. So in this example here, I'm saying array 9 gets np dot aRange minus 1.0 is going to be my initial value in this sequence. 3.0 is going to be just past the end of the sequence, and I'm using a step size of 0.5. So that means I'm going to get minus 1.0 as my first item, and then minus 0.5 as my next item, because we'll add 0.5 to minus 1 for our next item. The final item that we're going to have in our array is going to be 2.5, because if I were to add 0.5 to 2.5, I would get 3.0, which is past the end. So here we have array 9 starting with minus 1.0 and then increasing by 0.5 up to 2.5 and then stopping after 2.5. Alrighty? If we have an existing ND array, we can use a function called reshape to take a copy of that ND array and give me back an ND array with the same values but in a reshaped format. So reshape has to be performed on an existing ND array, and it does not directly change that existing ND array. What it does instead is to return to me those same values but in a modified shape. So let me talk this through. I'm going to create Gopher as an np.aRange with 10 items, and these are going to be integer items. So Gopher, by default, contains the integer values 0 through 9. And now if I say Gopher dot reshape, well, let me reshape that as a 2x5 array. All right, so I'm going to get 2 rows with 5 columns. And this is going to be now a 2-dimensional ND array of integer values. I could also say Gopher.reshape as a 5x2 ND array. So now I have 5 rows and 2 columns. For that matter, I can say gopher.reshape as 10 rows with just 1 value each. So this is actually a 2-dimensional array, but it's a 2-dimensional array in which each row only has 1 item. So it's a 10 by 1 array. If I wanted to change Gopher to contain or to refer to the reshaped version, then I can say, let's remind ourselves what Gopher currently contains. It's just the original array of integers, 0 through 9. If I say Gopher gets Gopher reshape 2, 5, well, Gopher.reshape 2, 5 is going to take the current contents of Gopher and reshape that into a 2 by 5 array. And then by saying Gopher gets that, what I'm doing is I'm changing the variable name Gopher to refer to this array that has the modified shape. Okay. Now, so we've looked now at several ways of creating or reshaping ND arrays. It would be awfully nice if we knew how we could access elements or items within this array. Well, it turns out that you use subscripting starting from 0, just like you can in a list. In addition to using notation like square bracket I, square bracket j to access a particular row and then a particular column within that row, we can, in Numpy, use the simplified notation that we would be used to using in mathematics of square bracket I comma j to access the ith row and the jth column. Again, everything starting from zeros. Okay, so here we still have array 8 sitting around, which is a vector. It's a 1-dimensional array containing 6 items, and therefore array 8 sub 3 is not the 3rd element, it's the sub 3 element, which is actually the 4th element. So the sub 3 element of this array is the value 3. Okay, and I can use negative subscripts as well. Array 8 sub minus 1 is the 5 at the end of the array. Here, in this next example, I'm generating a random integer array of 6 values. Okay, so NP has a module within it called random, and random in turn has a whole bunch of different functions for generating various kinds of random numbers according to a whole bunch of different kinds of statistical distributions. Rand will generate values between 0 and 1. So if I say rand 6, I get 6 random values between 0 and 1. Now, actually, in the half open interval, starting from 0 and going up to but not including 1. Okay? So 0 is a possible random value to get from this. 1 is just beyond the edge, or just beyond the end of what I could get. Now, each time I run this, I get, a different group of random values. Okay, now I can take this list of random values. I'm going to store it into, I'm going to use the name array 10 to refer to this. if I say np.random.rand6, this will generate a one-dimensional array, a vector of 6 random floating point values, and I can immediately take that and reshape it into 2 rows of 3 values each. So here is my array 10. All right. And I have different values than the values that are contained in the course notes here, because each time I ask for random values, I get different ones. But now that I have this array 10, I can access individual items. Like, suppose I want this item here in the lower left corner of array 10. Well, that is array 10, row sub 1, column sub 0. So array 10, bracket 1, bracket 0 will get me that value. But as a convenience, I can say array 10, 1 comma 0, and use the comma operator rather than the comma symbol rather than the separate square brackets for the dimensions. Okay, and that will work the same way for any of these items in this two-dimensional array. I can also ask for array slices, and these are very similar to how things work for lists. Let me just remind ourselves what array... Oh, I guess I'm recreating array 8 to contain random values this time. So array 8 is going to get NP... Oh, no, I'm sorry. No, it's not random values. So array 8, here it's being recreated, but I already have it. So I've got the integer values 0, 1, 2, 3, 4, 5. And if I ask for array 8 sub 3 colon 5, well, let's remember what that means if array 8 were just an ordinary list. It means get me the values from item sub 3 up to, but not including, item sub 5. So I'm going to get these two items, 3 and 4, item sub 3 and item sub 4, as the slice from the ND array. Now this slice will still be an ND array. Now another thing that you can do with ND array slices that will not work for ordinary lists is you can assign a scalar value, that is a number, or to all of the items in a slice with a single assignment statement. So here I'm saying array 8 sub 0 colon 3. All right, so array 8 sub 0 colon 3, that's going to be items 0, 1, and 2, that is items up to but not including 3. And this time, instead of just, well, let me display those just for, just to prove that I was correct there. And now if we say array 8 sub 0 colon 3 gets a -1, in NumPy, that actually will work. And what I get is array 8 modified to contain the value -1 in the first 3 items. Now, if we try to do this with an ordinary list, if I said m gets 0, 1, 2, 3, 4, 5, I should have used a comprehension, but it was too quick to type. Okay, so here's my m, and if I now say m sub 0 colon 3, that actually does give me back a copy of that sublist from item 0 up to but not including item 3. I cannot, however, with a list say 0 colon 3 gets -1. I get yelled at that thing on the right-hand side has to be an iterable, not a single value. So that is a key difference between slices in ND arrays and slices in lists. You can do arithmetic operations on ND arrays. We said at the outset of this discussion of Numpy that Numpy is a linear algebra library, and that's true. However, these ordinary arithmetic operations don't use mathematical array-wise behavior. Instead, what we're getting here by default is element-wise arithmetic, and the arrays involved have to have the same shape as each other. That is, they have to have the same number of rows and columns. If you want to, add two arrays together, they have to have the same shape, and if you want to multiply two arrays together in this element-wise arithmetic, they have to have the same shape, and so on. We can also do scalar operations on all of the items within an ND array. Let me show you some examples of this to make this a little more real. Okay, I'm going to create an array called A, according to the illustration shown here at the top of the page. And I'm too lazy to type this out, so I'm going to just copy and paste it in. All right, so there's A with 2 rows and 2 columns. 3, 2 in the first row, minus 1, 0 in the second row. And next I'm going to create B. And B will also have 2 rows and 2 columns. So here's B, okay? Now, if I say A plus B, I guess it shouldn't be a great shock what's going to happen. The element-wise addition accomplishes the same thing as if we did a matrix addition of 2 arrays that had the same shape. The resulting array that we're going to get will have 3 minus 2 is 1 as the sub-0 sub-0 item, and then 2 plus 1 is 3 as the sub-0 sub-1 item, and so on. So we get what we would have expected. All right. Likewise, A minus B is going to do element by element subtraction. So 3 minus minus 2, that's going to be actually a 5. 2 minus 1 is going to be a 1, and so on. So the addition and subtraction behave the same way in this default element-wise addition and subtraction as what we would expect if we did a matrix A plus a matrix B in matrix arithmetic. Where things change is if we say, let's remind ourselves, oh, well, we've got it. I'm going to do it again. Here's A, here's B. And if I say A times B, now in matrix multiplication, what you would expect is the first column of B to have the dot product perform with the first row of A to compute the value that you want for the sub-0 sub-0 item of the product. But that is not what happens by default with Numpy. Instead, we're just going to end up getting an array that has element by element multiplications. So 3 times minus 2 is going to be a minus 6 in the upper left corner. 2 times 1 is going to be 2 in the upper right corner. Minus 1 times 5 is going to be minus 5 in the lower left corner, and then 0 times 4 is going to be 0. Okay, so we are multiplying corresponding pairs of elements from A with those in B to get our result. Okay, so element-wise multiplication, not true matrix multiplication. Similarly, if we do division, A divided by B, well, we're really just dividing pairs of elements here. So 3 over minus 2 is going to be minus 1.5. 2 over 1 is going to be 0.2. Minus 1 over 5 is going to be minus 0.2, and so on. Okay, and then 0 over 4 gives me a 0. Notice that even though these original values are integers, when I do division, I always get floats. Okay, and so I've got floating point 2.0 and 0.0, as well as floating points for obviously minus 1.5 and minus 0.2. If I try to do the inverse division here, if I say b over a, well, this is going to end up being an error because a contains a 0 as one of its elements, and 4 divided by 0 is undefined. Okay, so I get warned that I divided by 0. Now, actually, rather than creating an exception, what happens is we get this value inf representing infinity for a divide by 0. Okay, now if the value in b when I do 4 divided by 0, if the value in b had been a negative number, I would have gotten a minus inf. Okay, so be cautious about accidentally doing division by 0. With scalar operations, the scalar multiplication or division, or for that matter addition or subtraction, is simply performed on an element by element basis. So here's my original a, hasn't changed, 3, 2, minus 1, 0 in the 2 rows. And if I say a times 4, then each element gets multiplied by 4. And there's my resulting array. And if I divide by 4, each element gets divided by 4. And here's my resulting a over 4. Well, actually, that's the same as ordinary multiplication of a scalar by a matrix, so that's not a big surprise. If I say a squared, a and then the exponent operator and 2, again, I want to be clear that this is not doing a matrix square. It's not a times a in a matrix sense. It's just going to multiply these individual elements by themselves. So 3 times 3 is 9, 2 times 2 is 4, minus 1 times minus 1 is 1, 0 times 0, 0 is 0. So that's the result that I get. I get told also that the data type of these things is int32. I'm not sure why I get that, because the data types of A itself is int32. So I'm not sure why displaying a squared shows me that as well. Well, whatever. If I say a, here's a. If I say a plus 1, that simply adds 1 to each item. And if I say a to the 0.5, that's going to compute the square root of each value in a. Minus 1, of course, is going to be a problem. So I'm going to get the square root of 3, the square root of 2, the square root of 0. Those are all fine. The square root of minus 1, well, Numpy doesn't have within it the notion of imaginary numbers. So what it does is tell me, well, sorry, no, that's not a number. All right, I get invalid value encountered in power, and nan stands for not a number. So again, it's not throwing an exception, it's not dying, but it's giving me a result that that I better be careful about trying to use. All right, so we've taken a look at the ordinary arithmetic operations, addition, subtraction, multiplication, division, and power, using 2 arrays as the operands. or using an array and a scalar as operands. There are also a bunch of mathematical functions within Numpy to do various mathematical functions on an element-by-element basis. Let me show you why this matters. You remember that we have functions like sine and cosine and exponent and log and so forth in the math library. So I might be tempted to say import math as m and then compute the sine of a. Well, unfortunately, this sine function in the math library only knows how to deal with scalar values. And so I get, yelled at that this is not going to work. But fortunately, I can use NumPy's sine of a, sine of a, to compute on an element-by-element basis the signs of each of the values contained in A. Okay. np.sum, by default, will compute the sum of all of the items there. But it turns out that I can use the axis keyword parameter to indicate that I want to do sums over, instead of doing the whole array, I want to do sums over just the columns or just the rows. All right, so if I say np.sum of a axis equals 0, this means that I want to get the I want to get an eddy array containing the sums of the columns. Okay, so notice 3 plus minus 1 is a 2, 2 plus 0 is a 2. Whereas if I ask for the sum over axis equals 1, this will give me the sum over the rows. Okay, so I get 3 plus 2 is 5, minus 1 plus 0 is minus 1. And this is a nuisance to have to remember that axis 0 means that you want to produce well, actually what you're doing is axis 0 means that you're summing over the rows, but the result is going to be the sums of all the columns. Axis 1 means you're summing over the columns. The result is going to be represented as row. You're going to get a value for each row. So the columns 3 plus 2 gives me a 5. The columns minus 1 plus 0 gives me a minus 1. And it's a nuisance to have to remember that. However, let me show you. Here's A. Remember, A's shape is 2 rows and 2 columns. Axis 0 is over the rows. Axis 1 is over the columns. So if you have a 3-dimensional array, let me do that. Let me create G as np.random.rand. Let's see. I want to create, to illustrate things clearly here, let me have 3 rows of 4 columns, and let's have our z. Okay, so we're gonna say like we're gonna have 3 rows, 4 columns, and then the final dimension is going to be a 5. So 3 by 4 by 5. So that's going to be 60. All right. So I'm going to get 60 random values, and I'm going to reshape that into 3, 4, 5. So here's G. And it's very, very messy to read. I guess I should have done something smaller. Let me say G gets np.random dot rand. Let's 2 by 3 is 6 times 5 is 30. Let's just have 30 values. I'm also going to use a round function that allows me to round to just, let's say, 3 decimal places, and then reshape to 2 by 3 by 4. Okay, 2 by 3 is 5 times 4 is 20, not 30. Cannot reshape array of size 20. I can't do math. All right, 2 times 3 is 6. So this should be 24. 6 times 4 is 24. Yay! I finally got it. There we go. So I have 2 as my first dimension, 3 as my second dimension, and then 4 as my third dimension. So I can think of this as being 2 levels in which each level has 3 rows and 4 columns. And if I ask for G sub, oh, let's say 1, 1, 1, 3, what is that? All right, well, that's going to be the first level, the sub 1 level, which is going to be this bottom 3 by 4 matrix. And the sub 1 row within there, and the sub 3 item. So we're going to get this, whoops, we're going to get the this item here. Okay, and so then if I ask for G dot shape, I get 2, 3, 4, and if I ask for G dot sum, this is all of the items. If I say G dot sum, axis equals 0, I'm summing over the levels, and I end up with a 3-row, 2-column sum. So 0.333, that level, plus 0.58, that level, is going to be 0.913, which it is. All right, well, I'm not sure that I clarified things, but that's what's going on. Okay, so onward ho. You just have to get used to this idea that axis 0 means the first dimension in your shape, axis 1 means the second dimension, axis 2 means the third dimension, and so on. Alrighty, just as a reminder, here's what A looks like. And if I want to compute e to the power of each of these items in A, I can say np.exp of A. All right, so here's 1 over e, and here's e to the 0 power, for example. np.fabs. Now, fabs is the floating absolute value. And so for -1, I'm getting 1.0 as my absolute value. And np.sign, I think I already showed you, but here it is again. Okay. Let me modify A now to be np.a range of 6, but reshaped as a 3-row and 2-column array. So it used to be 2 by 2, now it's 3 by 2. And if I say a.sum, I get the sum of all the items. If I say a dot sum axis equals 0, I get the sums of the rows on a column by column basis. So 0 plus 2 plus 4 is a 6, 1 plus 3 plus 5 is a 9. If I say a dot sum axis equals 1, I get the sums of the columns on a row by row basis. All right, so I get 0 plus 1 is a 1, 2 plus 3 is a 5, 4 plus 5 is a 9. And it turns out because axis is the first of the keyword arguments in the sum function, I can just say a dot sum sub 0. No, let me back up. Notice when I say a dot sum and hit parenthesis, that it shows me my little bit of documentation here, maybe just a hair below the screen for you. Axis is the first keyword argument, and because axis is the first keyword argument, I can actually leave out the parameter name axis, and I can just say sum over the rows or sum over the columns. I can also ask for the minimum of the entire array, or the minimum over the rows, or the minimum over the columns. Okay, let me display A again. So the minimum of the entire array is 0. The minimum over the rows, the minimum over the rows is going to be the minimum of 0 to 4 as my first column value, and the minimum of 1 through 5 is my second column value. If I ask for the minimum over the columns, then I'm going to get the minimum of 0 or 1 is 0, 2 or 3 is 2, and 4 or 5 is 4. And in addition to a min, there's also a max, which does the obvious thing. Okay, so continuing on, here we have A being recreated once again. There's just a reminder. I was using, and I think I did not emphasize this, these functions can be used as methods directly on the array. So I can say a.sum, a.min, a.max. Previously, when we were using trigonometric and logarithmic kinds of functions and other functions, we said np.exp of a, np.fabs of a, np.sine of a. You can do the same thing for sum and min and max. In addition to saying a.sum, I can say np.sum of a. And in addition to saying a.min, I can say np.min of a. All right, so it's convenient to be able to say things like sum, min, and max as methods invoked on the array. Here are some other functions that, for whatever reason, some of these you can invoke directly on the array and others you can't. I assume for historical reasons that a-min is just an alternate name for min. In fact, both min and a-min really invoke the same function. In fact, we can see that by saying np.min without the parentheses and np.amin without the parentheses, and you'll see that min and amin both actually execute the amin function. All right, so I guess amin was probably developed first, and then people were annoyed by that, and so min was created as an alias for amin. So I won't go through all of these examples here, but amin behaves the same as min. Mean produces the mean of the whole array. If you say np.mean of a, let me redisplay a so we know what we're talking about. All right, np.mean of a is 2.5. Does that make sense? Sure. 6 plus 9 is 15 over 6 is 2.5. And here's another one that you can invoke by invoking mean as a method on a. As we can with sum and min and max, I can say a dot mean of 0 if I want to do a sum over the rows to get okay, so 0 plus 2 plus 4 is mean is 2, 6 over 3, and 1 plus 3 plus 5 over 3 is 3, or a dot mean over the columns. Okay, the mean of 0 plus 1 is 0.5, 2 plus 3 is 2.5, 4 and 5 is 4.5. All right. Now, for whatever reason, there's also an average function that does the same thing as mean. So if I say np.average of a, I get the same thing as np.mean of a, and I can do sums over the columns, sums over the rows with average. I can't say a.average for whatever reason. Who knows? All right. Now, another thing that average will do that just plain mean won't do is you can apply weights to the different dimensions. So here I have A is a 3-row, 2-column matrix. In this example here, I'm saying I want to get the average over the rows, and I want to apply weights. Or I'm sorry, I want to get an average over the columns. Axis 1 is the columns, and I want to apply weights to those columns, a weight of 1 to the first column and a weight of 2 to the second column. So what I'm doing here is I'm going to compute 0 weighted by 1, so that's going to be 0 times 1, plus 1 weighted by 2, and that will be 2. And I'm going to divide that by the sum of the weights. So 0 plus 2 over 1 plus 2 is 3. And that's going to give me a weighted average of 2/3. Likewise, for the next row, if I'm going to average these columns. 2 weighted by 1 is 2. 3 weighted by 2 is 6. So that's going to be 8/3, which will be 2 2/3. And then finally, we'll get 4 2/3 for the final row of columns. All right, so this is np dot average of A over the columns with weights of 1 and 2. Okay, so you can do weighted averages using this average function. You can also read and write data files, both in text form and in binary form, directly using NumPy. I have, and let me pull up an ordinary notepad so that you can see this. I have in my, where is it going? Where is it? Okay, give me a moment. Okay, I'm back again. So I have in my course file directory this file called nums.csv. And this is a comma-separated value file. I'm going to open it with Notepad. There. So we can see that it's just 3 lines, and each line has 3 integer values separated by columns. Now, because it's a CSV file, if I double-clicked on it, it would get opened with Excel. But this is just an ordinary text file, and so in my code, I can now say, and I'm not going to manually type all this in. Let me copy and paste it from Notepad. Okay. So I'm going to say B gets np.genFromText of this nums.csv file with a delimiter of comma. Now you might argue that NumPy should be smart enough to understand that a CSV file is separated by commas, but unfortunately it's not quite that smart. So I do have to specify the delimiter character to be a comma. Now the good news is that you can specify other delimiters. So if you have files whose fields are separated by tabs, or files whose fields are separated by colons or semicolons or whatever, you can read those files in as well. When I do this, it doesn't work. Why? Hang on a minute. All right, so I bungled and I started my idle shell in a directory other than where my file is actually stored. So let me try this again. B gets np.genFromText, and I'm going to type in the full path name of where my file is found. It's in /users/jostland/ 90819. Oh, I can click there. All right. 90819 is our course number. A is our section. And A3 is our section. And 2022 is our year. And that's the directory where I've got this file stored. nums.csv. I've run out of space, but fortunately, I can just hit the Enter key because I am within a set of parentheses here, so I can just hit the Enter key and keep going on the next line down. And I'm going to say delimiter is a comma. Poof! Magic! And there we are. So even though when I showed you the file, you saw that the file contained 3 lines of integer values separated by commas, by default, these get read in as float values. And here is the shape. It is a 3x3 matrix. I can say np.saveText into, and I'm going to put it in the same place. I'm going to just copy and paste that. And I'm just going to call it new nums.csv. Out of space, so I'll hit my Enter key and keep going. Now, genFromText constructs an ND array and returns that ND array, which I can now refer to using this variable b. But for saveText, I have to specify the array that I want to store in the file. So I'm giving b as my argument specifying what array I want to store, and then I'm going to say delimiter is a comma. There, and I have saved the text. Now, let me show you in the file manager that that's been done. Okay, so here is new nums. I have successfully saved a copy of nums into new nums. However, if I look at that file, let me pull up that file in Notepad. Notice that those things are stored as floats rather than as ints. Okay, because by default, when I do when I'm interacting with when I use gen from text to get in integers, they actually get treated as floats, and when I use save text, they get stored as floats. Okay. You can also use a whole bunch of options. Now, gen from text, if you take a look at the documentation, has about 1 billion options. Let me scroll up my thing here. So if I say np.gen from text, notice this huge help message showing me all the various options that I can use to get gen from text. I can do things, for example, like skipping the header. It's entirely likely if you have a real CSV file that perhaps you saved as a CSV file from Excel, that the top line is actually going to be column names, and you don't want those pulled in as part of your numerical data. It's also possible that you have empty fields in your data, and you can specify a filling value of whatever you like. Now you got to be careful here. The example is filling values of -1, but you better think carefully about this because it's not at all clear that you really want -1s as a default value. The data type, you can also specify. The default for the data type is float, okay? And if you want int, you can say dtype gets quote int quote instead. In fact, that's what's being done here in this next example. Let me go ahead and type that in. So I'll regrow my shell window, and this time into B, I'm going to read from the same input file, nums, but I'm going to set the dtype equal to int, so that when I've read in B this time, it does contain int values rather than float values. All right, you can save and restore ND arrays as binary, and I'm not going to bother walking through this. You can say np.save of some array, and that will be put into binary by default, and the file will be given a .mpy extension automatically, and then you can load that back in. Okay, now everything that we've done with ND arrays up to now has been on an element by element basis. But let's take a look next at the actual matrix operations that we can do in Numpy that will enable us to do linear algebra operations on these matrices that we have. Okay, now in order for matrix operations to work, the shapes of the matrices involved have to correspond in an appropriate way. That is, if I want to do a matrix addition of two matrices, they both have to have the same number of rows and columns. Likewise, if I want to do a multiplication, a matrix multiplication of two arrays, the dimensions have to match up, and so let me show you what I mean by that. Okay, so if we're going to do a matrix multiplication, we have a couple of different notations we can use for this. We can say matrix 1 dot. Okay, this is a little confusing because we have a dot symbol, and then we have the word, the method name, dot, with the second matrix as an argument. Or I can use the np dot dot function with the first and second arguments. So let's create some actual arrays here that we can try these things out with. I think it will be a little more clear if I do real examples rather than just talking my way through these slides. So let us create the example shown here. Now I already have A as a 3x2 ND array, 0, 1 for the first row, 2, 3 for the second row, 4, 5 for the third row. Let me create B as an array, and I'll build this from a couple of lists. This is going to be a 2x4 array, so 5 minus 1, 0 minus 2 are the elements in the first row, and 9, 2, 4, 1 are the elements or items in the second row. And so here's B. So I can do a matrix multiplication of a 3x2 matrix times a 2x4 matrix, and I end up with a 3x4 matrix. You may recollect that if you have an M by P matrix and you multiply that times a P by N matrix, you get an M by N matrix. An M by N matrix as a result, okay? So the number of columns in the first matrix has to be exactly the same as the number of rows in the second matrix in order to be able to do matrix multiplication. Let's give that a shot. We're going to say np dot, and then the function name dot, a comma b. And there we are. We get the result shown here on slide 39. Okay, we started out with a 3x2 matrix multiplied by a 2x3 matrix, and we got a 3x4 matrix as a result. Now the first item here, the 9 in the upper left corner, is produced by doing a dot product of 0 and 1 with 5 and 9. So 0 times 5 is 0, 1 times 9 is 9, 0 plus 9 gives us our 9. And then for the second row here, the first item in the second row, that's going to be the second row of A times the initial column of B. So 2 times 5 is a 10, plus 3 times 9, which is 27, is going to give me 10 plus 27 is 37. All right, so hopefully you have done some matrix multiplication in the past, and so this, I hope, makes sense. Okay. I can, in Numpy, rather than using the named dot function, I can use the @ symbol as a way of doing matrix multiplication. So, whoops, sorry about that, messed that up. So I can say, whoops, I'll get this right. So I can say A and then an @ sign and B to accomplish the same thing as NP dot of the matrices A and B. So that's pretty slick. Remember that A times B, if you use the asterisk, that's going to try to do an item by item, element by element multiplication of A and B, and this will just not work because A and B don't have the same shape. So I'm going to get yelled at that these can't be broadcast together. That is, you can't do an element by element multiplication of a 3 by 2 array and a 2 by 4 array. Now, so just as a review here, let's suppose that A is 3 by 2, which it is, and B is 2 by 4, which it is. And suppose I also had an array called C, which is 3 by 4. Actually, I could create such a thing easily by saying C gets a matrix multiplied by B. And so C is now a 3 by 4 matrix. And we ask, okay, which of these multiplications would be legal? Well, we've seen that A dot B is legal because you can multiply a 3 by 2 array times a 2 by 4 array to get a 3 by 4 array. But most of the other combinations in here are not legal. I can't multiply A times C, all right, because the inner dimensions have to match, and they don't. Likewise, I can't multiply B by A, even though I can multiply A by B, all right, because 4, the number of columns in B, does not match 3, the number of rows in A. All right, so most of these are illegal. Now, down here at the bottom, though, notice that you can ask for the transpose of a matrix in NumPy by saying matrix dot T. So A is 3 by 2, A dot T is 2 by 3. B is 2 by 4, B dot T is 4 by 2. Aha, and C is 3 by 4, so we can multiply a 3 by 4 matrix times, do matrix multiplication times a 4 by 2 matrix. All right, so 3 by 4 times 4 by 2 is going to give me a 3 by 2 matrix as its result. And there we are. So I have a 3-row, 2-column result from multiplying C by the transpose of B dot T. And of course I can, as shown on slide 40 here, I can do this using the named dot function. Or I can say NP dot C B dot T. Alrighty. Right. Well, these are some simpler examples of what I just showed. I'm not gonna bother doing these simpler examples. Okay, so in these examples on slide 41 and 42, we've got versions of A and B that are just plain 2 by 2 matrices. You can give these things a try if you would like. I do want to remind you, if you don't know or don't recall, that unlike scalar multiplication in ordinary mathematics, and unlike element-wise multiplication in just plain NumPy with the star operator, matrix multiplication is not a commutative operation. That is, A matrix multiplied by B is definitely not the same thing as B multiplied by A. In fact, it's entirely possible that one of these will be legal and the other one will be illegal. recall in our case that A is a 3 by 2 matrix and B is a 2 by 4 matrix. So 3 by 2 times 2 by 4 is 3 by 4. But here, 2 by 4 times 3 by 2, well, that's not even defined because I can't multiply a matrix with 4 columns times a matrix with 3 rows. A times B works fine, but B, matrix multiplied by A, is illegal. Okay. Sometimes you would like to be able to multiply a vector times an array. Let me create D as a vector of 4 values. 4, 6, 7, 9. All right, so D is a one-dimensional thing. B is a two-dimensional thing. And I can multiply a 2 by 4 matrix times a 4 by 1 matrix. But I'm not going to be allowed to multiply a 2 by 4 matrix times a one-dimensional vector. Oh, that's hilarious. Okay. Okay, so apparently it expanded it out for me, and it just assumed that D could be treated as a 4 by 1 matrix. But if I want to officially change the dimensions of D, you can actually assign directly to the shape attribute sorry, this is going to be 4 by 1. You can actually assign to the shape attribute that you want the thing to be treated as a two-dimensional array. All right, so now D is a two-dimensional array, and so it makes consistent sense now, I guess, that oh yeah, it does make perfect sense, because now we have a 4 by 2 by... Oh, I messed this up. I messed this up. I meant to say D dot shape gets... No, I'm sorry. I did the correct thing. All right, so B shape is 2 by 4. And I have assigned D shape to be 4 by 1. So when I multiply the two, I should get a 2 by 1 resulting matrix, and I do. I've got a matrix here with 2 rows and 1 column in each row. Okay, so that gets us to the conclusion of this introductory information about NumPy. We can use NumPy either as just arrays of numbers that we can do element by element operations on, or we can use these arrays as vectors and matrices that we can do matrix operations on. And we can also do mathematical functions like e to the x, sine of x, log of x, absolute value of x, and we can do matrix-wise operations, in particular matrix multiplication in various forms, either using the ampersand symbol or using the dot function. All right. That's it. Talk to you on Tuesday, and I will actually physically see you on Tuesday, although I will also record the same lecture on YouTube and post it before Tuesday.